keys, and it's defined as follows. Basically here, the triple construction uses 3 independent keys, encrypts the same message block as before, and what it does is it will encrypt using the key K3, then it will decrypt using the key K2, and then it will encrypt again using the key K1. Okay, so it's basically encrypting 3 times using 3 independent keys. You might be wondering, why is it doing EDE? Why not just do EEE? Why do we have to have a D in the middle? Well, that's just for kind of a hack. You notice what happens if you set up K1 equals K2 equals K3? What happens if all 3 keys are the same? Well, basically, what would happen is one E and one D would cancel, and you would just get normal DES out. So it's just a hack so that if you have a hardware implementation of triple DES, you can set all 3 keys to be the same, and you'll get a hardware implementation of single DES. Of course, it'll be 3 times as slow as a regular implementation of single DES, but nevertheless, it's still an option. Okay, so for triple DES, in fact, now we get a key size that's 3 times 56, which is 168 bits. So this is 168 bits is way too long to actually do exhaustive search on. That will take time 2 to the 168, which is more than all the machines on Earth working for 10 years would be able to do. Unfortunately, of course, the cipher is 3 times slower than DES. So this is a real problem with triple DES. Now, I want to mention that, in fact, you might think that triple DES has security 2 to the 168, but in fact, there is a simple attack that actually runs in time 2 to the 118, and I want to show you how that attack works. Okay, so, but in fact, 2 to the 118 is still a large number. In fact, anything that's kind of bigger than 2 to the 90 is considered sufficiently secure. 2 to the 118 is definitely sufficiently secure against exhaustive search, and generally is considered a high enough level of security. So clearly, triple DES is 3 times as slow as DES. So the question is, why did they repeat the cipher 3 times? Why not repeat the cipher just 2 times? Or in particular, the question is, what's wrong with double DES? So here we have double DES. Basically, you see it uses only 2 keys, and it uses only 2 applications of the block cipher. And as a result, it's only going to be twice as slow as DES, not 3 times as slow as DES. Well, the key length for double DES is 2 times 56, which is 112 bits. And in fact, doing exhaustive search on a space of 112 bits is too much. 2 to the 112 is too big of a number to do exhaustive search over such a large space. So the question is, what's wrong with this construction? Well, it turns out this construction is completely insecure, and I want to show you an attack. So suppose I'm given a bunch of inputs, say M1 to M10, and I'm given the corresponding outputs C1 to C10. What's my goal? Well, my goal is basically to find keys, a pair of keys K1, K2, such that if I encrypt the message, the message capital M using these keys, in other words, if I do this encryption, this double DES encryption, then I get the ciphertext vector that was given to me. Okay, so our goal is to solve this equation here. Now you stare at this equation a little bit and you realize, hey, wait a minute, I can rewrite it in kind of an interesting way. I can apply the decryption algorithm, and then what I'll get is that I'm really looking for keys K1, K2 that satisfy this equation here, where basically all I did is I applied the decryption algorithm using K1 to both sides. Okay? Now, whenever you see an equation like this, what just happened here is that we separated our variables into 2 sides. The variables now appear on independent sides of the equation, and that usually means that there's a faster attack than exhaustive search. And in fact, this attack is called a meet-in-the-middle attack, where really the meet in the middle is going to somehow attack this particular point in the construction. Okay, so we're going to try and find a key that maps M to a particular value here and maps C to the same value. Okay, so let me show you how the attack works. So the first thing we're going to do is we're going to build a table. Here, let me clear up some space here. The first step is to build a table that for all possible values of K2 encrypts M under that value. Okay, so here we have this table. So you notice these are all, I'll say it like this, these are all 2 to the 56 DES keys, single DES keys. Okay, so the table has 2 to the 56 entries. And what we do is basically for each entry, we compute the encryption of M under the appropriate key. So this is the encryption of M under the all 0 key, the encryption of M under the 1 key, and then at the bottom, we have the encryption of M under the all 1 key. Okay, so there are 2 to the 56 entries, and we sort this table based on the second column. Okay, so far so good. So by the way, this takes time to build this table, takes time 2 to the 56, and I guess we also want to sort. Sorting takes n log n time, so it's 2 to the 56 times log 2 to the 56. Okay, so now that we have this table, we've essentially built all possible values in the forward direction for this point. Now what we're going to do is this meet in the middle attack, where now we try to go in the reverse direction with all possible keys k. Essentially, we compute the decryption of C under all possible keys k1. Okay, so now for each potential decryption, remember the table holds all possible values in the midpoint. So then for each possible decryption, we check, hey, is the decryption in the table, in the second column in the table? If it is in the table, then aha, we found a match. And then what do we know? We know that essentially, well, we found a match, so we know that, say, for example, a decryption using a particular key k1 happened to match this entry in the table, you know, k sub 2, or more generally ki, then we know that the encryption of m under ki is equal to the decryption of c under k. Okay, so we kind of build this meet in the middle where the two sides, you know, the encryption of m under ki and the decryption of C under K collided. But if they collided, then we know that in fact this pair, Ki and K, is equal to the pair that we're looking for. And so we've just solved our challenge. So now let's look at what's the running time of this. Well, we had to build a table and then sort it. And then for all possible decryptions, we had to do a search through the table. So there were 2 to the 56 possible decryption. Each search in a sorted table takes log of 2 to the 56 time. If you just work it out, this turns out to be 2 to the 63, which is way smaller than 2 to the 112. Okay, so this is a serious attack. It's probably doable today. That runs in a total time of 2 to the 63, which is about the same time as the exhaustive search attack on DES. So really, double DES really didn't solve the exhaustive search problem because, well, there's an attack on it that runs in about the same time as exhaustive search on single DES. Now, someone might complain that in fact this algorithm, well, we have to store this big table, so it takes up a lot of space, but, you know, so be it. That's nevertheless, the running time is still quite smaller, significantly smaller than 2 to the 112. Now, you notice, by the way, the same attack applies to triple DES. What you would do is you would implement a man-in-the-middle attack against this point. You would build a table of size 2 to the 56 of all possible encryptions of M, and then you would try to decrypt with all 2 to the 112 keys until you find a collision, and when you find a collision, you've basically found K1, K2, K3. Okay, so even triple DES has an attack that basically explores only 2 to the 112 possible keys. But 2 to the 112 is a large enough number, so triple DES, in fact, as far as we know, is sufficiently secure. I should mention that triple DES is actually a NIST standard, and so triple DES is actually used quite a bit. And in fact, DES should never, ever be used. If for some reason you're forced to use some version of DES, use triple DES, not DES. Okay, I want to mention one more method for strengthening DES against exhaustive search attacks. This method actually is not standardized by NIST because it doesn't defend against more subtle attacks on DES. But nevertheless, if all you're worried about is exhaustive search and you don't want to pay the performance penalties of triple DES, then this is an interesting idea. So let me show you how it works. So let E be a block cipher that operates on n-bit blocks. We're going to define the EX construction, and for DES we're going to get DESX to be the following. So we use 3 keys, K1, K2, K3, and then basically before encryption we XOR with K3, then we encrypt using K2, and then after encryption we XOR with K1. That's it. That's the whole construction. So basically, you notice it doesn't slow the block cipher much because all we did is we applied the cipher plus 2 additional XORs, which are super fast.